students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 8. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. This is our continuation of our series on carrier transport in semiconductor devices. Okay. So, let us continue our discussion. In previous lecture, we concluded with the topic of space charge effect. Okay. In that we had touched upon the topic of carrier injection. So, before we proceed into the details of today's lecture, let us just identify that the major objectives of any electronic device is to produce appreciable amount of current when a moderate level of voltage is applied across it. Okay. So, that is a major function of any semiconductor or any electronic device. Our discussion till now, whether it has been related to carrier concentration evaluation or identifying the current components or the polarity, okay, or mobility, these have focused around the condition of equilibrium. When we mention the situation of equilibrium, we are generally talking about thermal equilibrium, where the semiconductor does not have any external energy available except thermal energy. Okay. In such a case, your law of mass action n dot p equal to Ni square is also valid. This is the sort of equation where you can easily identify how many charge carriers are there, how many electrons are there in the conduction band per unit volume, and how many holes per unit volume are there in the valence band. Okay. But once a device is under operation, under practical use, it is difficult to say that it will be under the state of equilibrium. Okay. You have to apply some sort of an imbalance to these devices, so that you are able to produce the required amount of current. Now, this imbalance can be produced either through photo excitation, through impact ionization, or field assisted effect. Okay. So, with this we start the topic of generation and recombination of charge carriers. Whenever we apply a voltage to a semiconductor, some current starts to exist, okay, and we say that the semiconductor is operating under non-equilibrium condition. Suppose you apply forward bias across a p-n junction, you can say that you are injecting charge carriers via the external source. This is analogous to carrier generation. Excess electrons are created. Okay. If you create extra electrons in the conduction band and extra holes in the valence band, this is the situation which arises under non-equilibrium conditions. Okay. And this is in addition to the concentration of the equilibrium case. Okay. So, the expressions which we have seen till now for carrier concentration, those are your equilibrium values. Okay. And under the influence of external excitation, we are talking about non-equilibrium case. So, excess electrons and excess holes are present in such situation, and they do not move independently of each other. Okay. So, when extra electrons are created, it is quite possible that extra holes are also created at the same time. So, these excess carriers diffuse, drift, they recombine with the same effective parameters like diffusion coefficient, drift, mobility and lifetime. Okay. So, whenever the thermal equilibrium condition of a semiconductor is disturbed, okay, in that case your law of mass action is no longer valid. This is the expression for law of mass action, that the product of carrier concentration is a constant equal to Ni square. In this case, if non-equilibrium exists, there can be processes which try to restore this balance. Okay. So, if suppose n dot p is less than Ni square, then extra generation can occur, so that n dot p starts to become equal to Ni square, or if n dot p is greater than Ni square, this can lead to the so called process known as recombination. Okay. Thermal generation, now let us try to define this process of generation and recombination from the point of view of an energy band diagram. Okay. Suppose this line is representing the conduction band. Okay. So, above this you have the conduction band and below this you have the valence band, okay, separated by the so called forbidden energy gap. Initially you will have lot of holes in the valence band and very few electrons in the conduction band. Right. If you apply external energy, say things like photo excitation, some of the electrons might be able to reach the conduction band from the valence band. Okay. This happens when the applied energy is higher than the energy gap. This phenomena is known as generation of charge carriers. Okay. So, when electrons move from valence to conduction band, you increase the concentration of electrons in the conduction band, at the same time you increase the number of holes in the valence band. Okay. So, this is analogous to generation, and when this excess carriers in the conduction band, they come back to the valence band. Okay. This process is known as recombination. Okay. So, in order to in a better way to understand generation and recombination, let us define some symbols. Okay. So, we are going to refer to the thermal equilibrium concentration by this subscript naught. So, N naught and P naught are your equilibrium concentration, N and P are your total carrier concentration. Okay. So, at equilibrium N is equal to N naught. If there are excess charge carriers, they add up. Okay. And these excess charge carriers can be a distance of can be a function of distance as well as time. Similarly, total hole concentration is equal to the equilibrium concentration plus if we have generated any excess holes, which is a function of distance as well as time, either one or both. Okay. So, delta and delta P are your excess charge carriers, these are over and above your equilibrium concentration. Gn and Gp refer to the rate of generation, at what rate carriers are being generated. So, N for electrons, P for holes. Rn and Rp your recombination rates of charge carriers, the rate at which these charge carriers are recombining. Okay. And finally, we define tau subscript N naught and tau subscript P naught. You know, tau is usually used for time parameter. So, here also it refers to the lifetime of these excess charge carriers. Just keep in mind here that we have used the word minority. Okay. We could have only used excess carriers, okay, but we would see later on that whenever excess charge carriers are generated, in percentage terms the concentration of minority charge carriers go up significantly, and the percentage change in the majority carrier concentration is very less, almost negligible. Okay. So, the time for which these excess charge carriers are alive before recombining, that is basically their lifetime, right. So, electrons in the valence band may be excited to the conduction band. Okay. This can be via photogeneration, via ionization, impact ionization, or apply external electric field. When this happens, you create an electron in the conduction band which leaves behind equal amount of holes in the valence band. These additional electrons in the conduction band and additional holes in the valence band, these are known as your so called excess electrons and excess holes. Okay. And these are obviously generated by some external force at a particular rate. For the direct case, we refer to as band to band generation, which means electrons directly go from the valence to the conduction band. There is an indirect case also possible where the charge carriers initially go to a defect state inside the forbidden gap and then they go to the conduction band. That is an indirect case of generation, but let us limit our discussion to the direct case. Okay. So, the rate at which electrons are generating in the conduction band, at the same time holes are generating in the valence band. Okay. And when excess carriers are generated, the concentration of electrons in the conduction band goes up above the equilibrium level, and concentration of holes in the valence band also go up above the equilibrium level. So, the net total electron concentration is equilibrium plus excess, net hole concentration is equilibrium value plus excess. Okay. So, law of mass action is only valid when there is thermal equilibrium, that is N naught dot P naught equal to N I square, this is valid. Okay. And at equilibrium N is equal to N naught, P is equal to P naught, but when excess charge carriers are present, then N dot P may not be equal to N naught P naught. Okay. So, the excess electrons then they recombine also. So, for the direct case, these electrons in the conduction band, excess electrons, they come back to the valence band and recombine. Okay. That is referred to as direct recombination. So, the rate at which they generated, it was equal for electrons and holes, the rate at which they recombine is also equal for electrons and holes, right. So, electrons moving from valence to conduction band, that is generation, electrons moving back from conduction to valence band, that is recombination. For the direct case, the rates at which this generation and recombination is taking place is same for both electrons and holes. The excess carrier electron concentration is equal to the excess hole concentration for this case also. Okay. So, let us just do a bit of maths related to it. The rate at which recombination is taking place. So, the rate of recombination is proportional to the carrier concentration. That is quite logical, because until and unless you have excess charge carriers available, there is not going to be any recombination. Recombination is only going to happen in the presence of these excess carriers. Okay. So, the net rate at which, say we take the example of electron concentration, the rate at which this electron concentration is varying with respect to time is proportional to what? Ni square, okay, n dot p, or I should say n naught dot p naught minus whatever is in the excess. Okay. And this constant of proportionality is known as recombination constant or recombination coefficient, denoted by alpha r. Okay. And this parameter, this small parameter here, alpha r Ni square, this is nothing but the generation rate. Okay. So, this is the rate of generation minus whatever is present. Okay. So, n, as we have seen earlier also, this is the total electron concentration, which is a function of time, because excess charge carriers are alive for a finite amount of time, they have a finite lifetime. Similarly, hole concentration is now also a function of time. Just keep in mind here that the equilibrium concentration n naught and p naught, equilibrium concentration of electrons and equilibrium concentration of holes, is not a function of time. Only delta n and delta p are function of time. Okay. And since we are talking about the direct generation and recombination case, the rate at which electrons are generated is same as the rate at which holes are generated, same for recombination. So, excess electrons is equal to excess holes, right. So, if we have this equation for rate of recombination, okay. So, n dot p I can write, I can expand it like this, n is equal to n naught plus delta n, p is equal to p naught plus delta n. So, my rate of recombination becomes like this. If I expand this bracket, I am going to see a term here where there is alpha r Ni square minus n naught p naught, okay, and minus n naught del p minus p naught delta n and minus delta n and delta p. Okay. Now, this n naught p naught is equal to Ni square as per law of mass action. So, this term is going to cancel to 0. Okay. We are only left with this term, and you can sort of reduce this term by making a small assumption which is known as low level injection. Okay. So, we make a small assumption which is known as low level injection, which is quite a reasonable assumption, because in any semiconductor, if you say that the excess charge carriers, especially the minority carriers, is small as compared to the majority carrier concentration, then this assumption is valid, which basically means that if this is an n type semiconductor, or say if this is a p type semiconductor, the minority excess electrons will be quite less as compared to the majority hole concentration. Okay. So, in percentage terms, whenever excess charge carriers are generated, the actual concentration of minority carriers goes up significantly, but the concentration of majority charge carriers remains almost constant. Okay. And this excess minorities are very small as compared to the equilibrium majority concentration. Okay. So, this is referred to as the case of low level injection. In this assumption, first of all, you can ignore this product of excess charge carriers, which is a very small number. Okay. And for a p type semiconductor, you can ignore this, and for a n type semiconductor, you can ignore this. Okay. Because for a p type semiconductor, the minority electrons and the majority holes, this product will be more suitable. Okay. So, for a p type semiconductor, you can write the rate of recombination. Now, we have also deviated slightly, here we are using n, here we are using delta n. Okay. This is because we are differentiating with respect to time, and n total concentration, which is equal to n naught plus delta n t. Here n naught is independent of time. Okay. So, n can be replaced by delta n here. Right. So, the rate at which excess charge carriers are recombining, this comes down to this equation for a p type semiconductor. Okay. And this is a standard differential equation with a standard solution given by this. Okay. Where this term 1 by alpha r p naught, alpha r is recombination constant, p naught is the equilibrium concentration of holes in the p type semiconductor, and this ratio 1 by alpha r p naught is what is the excess minority carrier lifetime, or you can say excess minority electrons lifetime. Okay. This is for a p type semiconductor. So, recombination of excess minority carrier electrons can be written as negative sign of the rate at which they are recombining. Okay. This negative sign basically means that with respect to time, the concentration of excess electron goes down. Okay. So, with time, when they are generated, when excess carriers are generated, with time they tend to recombine. Okay. So, that is why there is a minus sign here, and this we have already seen that this is the solution for this. Okay. So, this equation basically tells you the rate of recombination of charge carriers. Okay. We have done this for a p type semiconductor. For an n type material, okay, where there are lot of electrons as compared to holes at equilibrium, again we make the assumption of low level injection, which says that the minority holes being generated in excess is quite less than the majority electron concentration. The decay of minority holes occurs with the minority carrier lifetime given by this equation. The analysis is same for both n type and p type semiconductors, and this is your rate of recombination. Okay. So, in any extrinsic semiconductor under low level injection, the effective diffusion coefficient and mobility parameters are actually dominated by minority carriers. Okay. So, we proceed further. From the generation and recombination point of view, we see another mechanism which is known as thermionic emission. Okay. Now, as our topic is advanced semiconductor devices, so we have to go through different mechanisms, not only standard drift and diffusion. There are multiple mechanisms which exist inside an advanced semiconductor device. Like in the last lecture, we have done what happens at very high electric fields, that your drift speed is no longer proportional to electric field. Okay. Mobility degrades at high electric fields. Similarly, there is another mechanism which is known as thermionic emission, which is not a undesirable effect, but it is actually the mechanism with which many devices operate. Okay. This current mechanism or carrier current mechanism is related to majority charge carriers. So, electrons in n type, holes in p type, and it is always associated with a potential barrier. Say for example, a Schottky condition where you have a metal semiconductor interface, that is a Schottky interface. Okay. In such kind of devices where these kind of interfaces exist, like between a metal and a semiconductor, you can have thermionic emissions. Such kind of mechanism requires the barrier width to be very narrow. Now, if one side is metal and another side is semiconductor, you are only going to have the depletion region on the semiconductor side, and if you keep increasing the forward bias, that depletion region also reduces. So, the barrier is quite narrow and it is of the order of the mean free path. Okay. Or say for example, a triangular barrier where the slope is quite steep. Okay. In such kind of devices, you can have the mechanism of thermionic emission. After you have injected charge carriers, say by applying a voltage, diffusion in that region should not limit. Okay. So, the region beyond the metal should either be n type, or the region beyond p type should either be a metal. Okay. So, either you can have a p type metal interface or you can have a metal n type interface. Okay. In such a scenario, you are going to have thermionic emissions taking place, right. And in accordance with Fermi-Dirac statistics, the electron density falls above the conduction band edge. So, as you keep going above conduction band, the probability of finding electrons tends to reduce. So, electron density tends to reduce. Okay. But carrier density in conduction band is not 0, okay. It may be small, it is not 0, provided that temperature and energies are also not 0. So, the thermally generated charge carriers with energy above the barrier height, okay, which barrier height? This barrier height which we are talking about. So, you can have semiconductor here and metal here, okay. This barrier height above that. So, thermally generated charge carriers which are managing to cross the barrier, okay. The current produced by these charge carriers, the current density is given by this equation, okay. And you can say that this equation is dependent on the barrier height, the so called Schottky barrier height, okay. Temperature, Boltzmann constant, okay, and another constant A star which is known as the Richardson constant, okay. And this is also dependent upon Boltzmann constant and Planck's constant, effective mass and charge, okay. So, this sort of tweaks the actual current density equation. So, if you apply the standard drift mechanism and you get some equation for current density, it might deviate slightly from that value, because in situations where you have a very steep barrier, potential barrier, okay, where the width of depletion region is very small, or in a Schottky interface where depletion region only exists on the side of the semiconductor. These sort of situations which are common in many advanced semiconductor devices, current density is because of thermionic emissions and it changes slightly, okay, and it is inversely proportional to the exponential of barrier height, okay. In addition to thermionic emissions, many modern semiconductor devices work on the principle of tunneling, okay. Now, whenever there is an energy barrier, potential energy barrier, classical mechanics would tell you that you have to apply an energy at least equal to that potential barrier height, okay, so that charge carriers are able to surmount this barrier and move to the other side and produce current. There is another possibility that instead of crossing the barrier, the charge carriers actually tunnel through the barrier, okay. This phenomena is known as quantum tunneling. So, in quantum mechanics, we can say we use the wave function psi. In one of our initial lectures, we did the concept of quantum mechanics and we introduced the wave function psi. The psi can be defined in regions which are to the left of the finite barrier and to the right. Let us call this as region 1, region 2, region 3. If you solve Schrodinger's wave equation in these 3 regions, you are going to get the solution and you are going to get the expression for psi. The solution of Schrodinger's equation is going to give you the expression for psi, and you would see that in the regions outside this barrier, psi does not terminate abruptly, but it can exponentially decay, okay. Which means, so this is the pattern for psi, okay. This is how it is going to look like, which basically means that since psi square is going to give you the probability of finding electron, okay. There is a non-zero probability of finding an electron outside the barrier, even if the total energy of the electron is less than the potential barrier height, and this is the phenomena of quantum mechanical tunneling, okay. So, this is your psi wave function, this is how the expression it looks like, okay. So, it is imaginary where alpha is given by this effective mass, total energy, potential barrier height and reduced Planck's constant, okay. For tunneling to occur, we have to make an assumption that total energy is less than the potential barrier height. If it is higher, classically it will anyway go through, okay. So, tunneling probability is also defined as the probability density function or psi square in region 3. What is region 3? This is your region 3, this is your region 1 and this is region 2, okay. So, electrons does exist inside this region in a finite potential well. It can exist outside these regions also, even if its total energy is less than the potential barrier height q v naught, okay. So, this is basically what is the phenomena of quantum tunneling is all about. Many major devices work on the principle of tunneling. You can have tunnel diodes, okay. You can have tunnel FETs which does work, and it is only quantum mechanics which is able to define this phenomena, where it says that electrons instead of surmounting a barrier, they can pass through a barrier, okay. And this is the phenomena of quantum tunneling. So, these are some of the references which you can refer to for seeing the content which has been covered in this lecture. So, we have covered a very important concept of how excess charge carriers are generated inside a semiconductor and how they recombine. We have seen how thermionic emissions take place, and we have seen how tunneling allows current to flow through even if the total energy is less than the barrier height. Okay. So, with this we conclude this topic also on carrier transport, and we are going to continue our discussion on advanced semiconductor devices in our future lectures. Thank you for